So anyway, our next speaker is Eric Schnetter from the Perimeter Institute. Eric is the author of the Carpet driver, which is possibly the most important fundamental piece of computational infrastructure currently in the Einstein Toolkit. The Carpet AMR driver is probably responsible at one point for being the most using the most cycles in the Exceed network for simulations. And we are excited to have him talk here this afternoon about CarpetX, a new direction for doing AMR within the Einstein Toolkit framework.
Thank you. Good afternoon. I'm a computational physicist working at the Perimeter Institute for Theoretical Physics. And this talk, I kind of expected this talk to be given at the end of the meeting. Since at the beginning of the meeting, some of the concepts that I want to use haven't been introduced yet. So I split my talk into two. In the beginning, I'm giving a review of how Cactus looks internally and the various concepts. That is probably a good tutorial. And in the second half, I talk a bit about the design of CarpetX, the new driver that should be better, faster, shinier than the current Carpet driver. And please interrupt me at any time. Zoom meetings tend to be a bit tedious otherwise. I feel like speaking against the wall. So you can type something in the chat and someone will interrupt me and ask the questions. That is just fine. So let's begin with the Cactus framework. As Steve mentioned this earlier, the Cactus framework consists of the flesh, the part in the middle, and the thorns around them. And the thorns are the modules or the packages that do the actual work. So some of the thorns, for example, solve the Einstein equations, look for horizons, extract gravitational wave signals, hydro equations, perform neutrino transport, etc. And there are also other thorns that are more infrastructure packages. For example, there's a thorn for time integration called method of lines. And that's actually an interesting idea. That means when you solve the Einstein equations and the hydrodynamics equations, these thorns don't do their own time stepping. There's one common thorn doing the time stepping. And that means all the physics is evolved with the same time integration algorithm using the same time step sizes automatically. That makes it easier to write the thorn to solve the Einstein equations and also makes it easily possible to couple all these thorns together that I had on the left-hand side. But you have not only these numerical algorithms, but also more low-level things. For example, memory management, allocate memory for the metric and whatever you want to store. There's an algorithm called adaptive mesh refinement that needs to be implemented, parallel efficient I/O, and so on. And these three things, these infrastructure things that are more computer science than physics or mathematics, these are in Cactus performed by a special thorn called a driver. And Carpet and CarpetX are drivers. So I want to talk a bit more about what a driver is and what it does. I'm sorry, I got the order of the slides wrong. Apparently, I'm going to talk about adaptive mesh refinement first. That's the numerical method that we want to use to solve the equations. If you want to discretize spacetime, you can put a uniform grid over it. For example, here, this black grid. I hope you can all see the mouse. If not, please complain. But sometimes you might need a higher resolution. You might need more accuracy in certain parts of the domain. And in adaptive mesh refinement, what you do is you look at the solution, you determine whether you have enough accuracy. And in the places where you lack accuracy, you put a finer grid. For example, here 2 blue grids and even 2 red grids that give you an even higher accuracy. That's, of course, is just a schematic graph. Here on the right-hand side is an image taken from the AMREX documentation from an actual time evolution where you see 3 levels of adaptive mesh refinement. And you see that the refined meshes track quite nicely the shape of the blob that is evolved here. And the large boring regions of the domain where the red grid exists, there you don't need resolution. And that makes things much more efficient, much faster. So the basic idea behind adaptive mesh refinement, and that's the main algorithms implemented in Carpet and CarpetX and in AMREX, is to put the resolution only where it is needed. While you run the simulation, from time to time, you look at the current state and you change the grid structure so that you only refine these places where you need. That is called regridding. And that gives a very significant speed up. But the disadvantage is that when it comes down to all the details, it's a rather complicated algorithm. That's also why the algorithm is confined to being in a single thorn in Cactus, as opposed to every physics thorn having to do bits and pieces of it. So you see that the refined regions here, the blue and red ones, they all look like rectangles. That is, the physics thorns can live in a fantasy world where the whole domain looks like a rectangular domain, or blocks of rectangular domains that could be implemented even in Fortran in 1977. And the complex mechanisms necessary to put everything together, that is handled by the driver. Makes it much simpler to write physics thorns. And as an example, when we evolve black holes, we often use something like 8 levels of mesh refinement, and the potential speed up is then significant. If each level is refined by a factor of 2, if you refine 8 times, you refine by a factor of, is this correct? You refine by a factor, no, that number is completely wrong. Then you refine by a factor of 256 in each direction, but you're refining in all 3 spatial directions, plus also possibly in the time direction. So the overall refinement is something like 256 to the 4, not 8 to the 4. It's much, much larger. It's millions or billions what you save. So many problems are completely unfeasible without any kind of adapted coordinate systems or adaptive mesh refinement. So I don't know what I was thinking when I wrote 4096 here. The actual potential speed up is much, much larger. And I also want to briefly review what ghost zones are. Steve mentioned that this morning already. So ignore the different colors of the different grids here. These are only for OpenMP parallelization. I will discuss that later. We have here one coarse grid, the white grid, and 2 refined grids, the box here on the left and the square here on the right. And if you want to solve a partial differential equation, you might need to calculate a derivative. And calculating derivatives, if you use finite differences, require information from neighboring cells. So say you know the solution here at this point and you want to calculate the derivative in the x direction. One very simple method is that you, where's my mouse cursor here, that you look at the left point and look at the right point and to look at the function values here and draw a line through that, and thus you can estimate the derivative of the function at this point here. And this, what I described, is a 2nd order method. There are also 4th order, 8th order methods that are much more accurate. Of course, you have a problem if you want to do that at the boundary of the grid here, because there is no point here on the left. And what Ambrex and what Carpet and Cactus do is they provide ghost zones. I'm showing that here. That is, the grid on which you calculate is still the one in this black line, but the actual grid that exists in memory is a bit larger. Here it has one more layer around. And these are called ghost zones. And ghost zones is not where you calculate something. You can only read them. And they're defined, they're written by the framework. And this allows you to calculate the derivative everywhere. For example, you can calculate the derivative here by looking at the value in a ghost zone. And ghost zones need to be filled by the driver. If there's a neighboring fine grid, for example, from here to here, then you can fill the respective ghost zone by copying data from the neighboring grid. So you need to know which grids are neighboring each other. And in other times, when there's no neighboring fine grid, you need to look at the respective coarser grid, and then you need to interpolate the data there to get values here onto the respective fine grid point. And of course, the exact algorithms about how you find neighboring grids and how you interpolate and finding out from where to interpolate, that is all handled by the driver, because the driver has the respective information. And that's at the heart of the details of the AMR algorithms. So let's review that. There are 2 main parts of the AMR algorithm. One is called prolongation, one is called restriction. Prolongation means you interpolate data from the coarse grid to the fine grid. The name prolongation comes from the idea of vector spaces. Functions form a vector space, right? Function spaces are vector spaces. So all the data living on the coarse grid, they form a vector space, a discrete function space with a certain size. And if you imagine the whole coarse grid is refined, covered with a finer grid, then the finer grid has 8 times as many grid points in 3D. So it's kind of a longer vector. The vector space is 8 times as large, hence the name prolongation, to go from the coarse to the fine grid. And the opposite is called restriction. If you have data on the fine grid and want to update the respective coarse grid at the same location, that's called restriction. And so far, I only hinted at changing the resolution in space, but you can also change the resolution in time. You have two choices. One is you use the same time step size on all the grids. That's simple and scalable. And the other is that you realize that if you solve a hyperbolic equation, then you can take much larger time steps on coarser grids. So if you have 8 levels done on the coarse grid, you can take a time step size that is 256 times as large. And that, of course, that reduces the amount of the computational cost by a factor 256 on the coarsest grid. So this is called subcycling in time. That means you take large time steps on the coarse grid, small time steps on the fine grid. And that is a complex algorithm, but in the end, it can be more efficient than not using subcycling in time. And the rule of thumb is if someone tells you they're using adaptive mesh refinement, if they don't mention subcycling in time, they don't do it because it's really complicated to get right. And if they did it, they would tell you about it. So if you're asking yourself whether we're using subcycling in time, I already answered the question. Let's go to a bit more details. These are two figures I took from the Cactus documentation that's available on the archive. Here on the left, you can see again how the grids look with ghost zones and not. So let's say the red points here. I wish my mouse cursor wouldn't vanish all the time. These red points here, and then in between you have the fine grid points, and you see some fine grid points might lie on top of a coarse grid point. You can just use the same value here, and others lie in between, and then you need to interpolate. Here you could use, for example, linear interpolation in one direction, and here you would use a bilinear interpolation from the 4 neighboring points here. And these hollow points here are the edge of the fine grid. These actually are the ghost zones on the fine grid. They need to set from coarser grid data, etc. And that arrow here has to do with boundary condition. I'm going to skip that here. I think I should have used the simpler figure for this presentation. And when it comes to subcycling in time, it's actually a bit more complicated. I'm going to describe it anyway, but if you don't get all of that, don't matter. It won't matter for the rest of the presentation. So here, time goes up, space goes left and right. So this is a coarse grid, the red one here with coarse grid points, where you take a coarse grid time step. And in the fine grid points here, you take fine grid steps, which are smaller. So the subcycling in time algorithm invented by Berger and Oliger goes as follows. First, you do a coarse grid time step on the coarse grid. Then you do a fine grid time step that only gets you half as far. And then if you have ghost points on the fine grid here, you can interpolate them both in space and in time, because on the coarse grid, you know the future value, and the past values you can interpolate in time and fill up the hypothetical ghost point that is here, that is not drawn. And third, you take another fine grid time step. Now, coarse and fine grid are aligned, but you might actually have points that exist in both on the coarse and the fine grid, and you want to keep them consistent. So then you perform the restriction from the fine grid to the coarse grid, assuming the fine grid data are better. So whenever you have both coarse grid and fine grid, you just copy from the fine grid to the coarse grid, ensuring they both have the same data here. This is with 2 levels. If you have more levels, then you do the same thing recursively with fine grid, coarse grid, fine grid, even finer grid, and so on and so forth. And the figure here shows how interpolation goes. This ghost point here on the fine grid. Left, I now realize we changed left and right in this figure. Now red is on the left and green on the right. That incredible. Yeah, that paper was written 9 years ago. This point here is only interpolated in time, and this point here is interpolated both in time and in space from these 4 points here. If you actually want to do it consistently and ensure it's discretely stable and so on, there is a lot more to be said, and there are quite a few papers written on top of that. But that's the general gist of the idea of subcycling in time. Now, I briefly describe Carpet, the current Cactus driver that many people use for adaptive mesh refinement, what a driver actually does. So when you write a Cactus thorn, you're only writing a package, a module that does a small bit of a simulation, doesn't do everything. For example, you only solve the Einstein equations. And of course, you need to access T mu nu, which appears on the right-hand side of the Einstein equations. So if you also do some hydrodynamics, you might have to look at the hydrothorn, what it does there. So each thorn describes how it interfaces with other thorns in so-called CCL files. And the driver examines these CCL files via information passed from the flash and then drives the simulation. For example, the driver calls the various physics functions at the various times. In the beginning, it calls the initial data functions. Later on, it evaluates the right-hand side, calls the time evolution thorn, etc., calls the I/O routine. Which function is called at what time? That's all decided by the driver, all kept consistent. It also allocates the memory. For example, if you change the grid structure, you need to allocate new memory for the new grids that you create. You have to delete the old grids and so on and so forth. And the driver also implements the adaptive mesh refinement algorithm. That's where the numerical detail comes in. The driver also does everything that has to do with parallelization. For example, the parallel I/O, writing things to disk and reading them back in, interpolation, reduction. You're going to hear more about that in the coming days. And Carpet is parallel. It's parallelized using both MPI, that's distributed memory parallelism, and OpenMP, that's multi-threading within a node. And Carpet scales to more than 10,000 cores. So that means if you use Carpet on 1,000 cores, you're probably happy. If you're using it on 10,000 cores, then yeah, you can still do it. And if you run it on 100,000 cores, then you're a bit in a bit of pain. It's still possible, but you need to be much more careful. That was Carpet. Now let's switch over. The logo is all new, different color scheme. CarpetX, that's a new Cactus driver based on AmRex. And AmRex is a library that I'm going to describe on the coming slides. The basic design of Carpet was as following. There is CarpetLib at the lower level. That's a generic library that's independent of Cactus that just provides adaptive mesh refinement. It handles grid structures and does the interpolation, prolongation, reduction, restriction, etc. And there's Carpet sitting on top of that. That's the actual driver that knows about Cactus and everything, and all the lower level tasks are just passed on to CarpetLib to do the actual heavy lifting of the stuff. And CarpetX is a redesign of Carpet. Started about a year ago, a group of us. The idea is to replace CarpetLib by AmRex, because AmRex turns out is in its design very similar to CarpetLib, but it has certain advantages. And at the moment, CarpetX is close to production ready. I can show you movies, but you can't yet do a binary black hole coalescence and get waveforms out. So AmRex, stealing from their website, is a software framework for massively parallel block structured adaptive mesh refinement. That's exactly what Carpet is as well. And if you look at the history of all the libraries that support adaptive mesh refinement, etc., both Carpet and AmRex trace back to a library called BoxLib that was invented, I don't know, 20 or 30 years ago. So all the design ideas are kind of similar. Of course, the code is very different. But since the design ideas are similar, it's kind of straightforward or not too complicated to retarget the code. So AmRex, the advantage of AmRex, it's funded by the DOE. That's a good thing. It targets exascale computing. All the right buzzwords are there. And it's used by many applications. It's actively developed, and we're collaborating with the AmRex team. And that has a ton of advantages for us, because that means if we're looking for a feature, then probably means that 10 other research groups outside the Einstein Toolkit are also looking for that feature. That makes it much easier to implement it. Also, if we implement a new feature, then suddenly it's available to a much larger group of people. And in the spirit of Einstein Toolkit and open source, that is actually quite satisfying. For example, higher level prolongation and restriction operators are difficult and tedious to implement. And making that word and having that used by others, it is much easier to get funding for that, NSF funding, for example. So now I want to describe the features of CarpetX. And if you haven't used Carpet before, that might hang in the air, a description of these features. So I'm going to try to ground it a bit. But if you've used Carpet before, then I hope these features excite you. So the most important features, and Steve Brand should be very proud about that because that's his brainchild, is that CarpetX has sophisticated consistency checks that prevents and detects many errors that you might make when using the code. I mentioned earlier that these dawns are written in isolation and the driver decides which function to call at what time. And it's actually difficult to get that correct. It can well be that one thorn expects the boundary condition of the metric has been set, but no other thorn has provided a boundary condition, and then you access uninitialized variables. And maybe that just things happen in the wrong order. First they're accessed and they're written later on. And then if you look at the output, you might not even know what is going on. So the thing that CarpetX now does with the help of the infrastructure that Steve Brand developed is it meticulously tracks which part of what grid function is defined when and which operations invalidate these things again. And that means you actually have to update the thorns that you write. So here the large text on the right is part of the schedule entry for the right-hand side of the Z for C thorn. That's the solves the Einstein equations in the zeta for C formalism. So it says the thorn is written in a language that is C, well, it's actually C++, but it has the extern C declaration around it. And then it exactly says what it accesses. So it lists all the variables that we have here, chi, gamma, k hat, a tilde, gamma tilde, and so on. And it accesses these everywhere on the grid. And then it writes the right-hand side variables, but only in the interior. It can't fill the ghost zones or the boundary points because you can't evaluate derivatives there. So some other routine must do that later. Either a boundary condition that is scheduled, or you use periodic boundaries, or the driver has to synchronize or prolongate things at the boundary. This routine doesn't care. It just says what it does and what it doesn't do. And the driver actually checks. So the driver checks actually the boundary of, say, chi right-hand side here. And if the routine modifies chi right-hand side, then it's an error. The driver has an option to calculate checksums of all the points that the routine is not supposed to use. Of course, that's only used in debug mode, right? It doesn't slow things down when you run on production. But the driver would also initialize the interior of chi right-hand side with nans. And then if the thorn has written it and there's a nan left over, then the routine here hasn't actually initialized all the interior points. And another thing that is wrong. And any variable that is not listed here cannot be accessed by this thorn. And these variables that are only declared to be readable, they're actually constant, so they can't be written. That's a compiler error and so on. And half of these things, you know, that's typical things that compilers can already do, but other things are quite sophisticated. And this was very useful in development, and even was driven to implement good error messages for that, because I was running against these when I was writing physics thorns. And when I just implement the driver CarpetX, and then I write a physics problem, and then I have trouble understanding the error messages. That only shows you how difficult it is to get these things right. And I believe that is one of the biggest disadvantages of Carpet and the current state of the Einstein toolkit, that these inconsistencies are difficult to find and difficult to remedy. So if there's no other reason, if you don't care about AMREX or anything else, this should get you excited if you're a current user of the Einstein toolkit. And if you're not using it and see how bad and difficult it is, I'm sorry. I know it should be easier. It will be easier with CarpetX, but cutting edge physics you always have to invest into getting things correct. It remains tedious, unfortunately. The second thing, of course, is that everybody talks about as the first thing, the improved scalability. Exascale systems, so we're expecting to scale to more than 100,000 cores. We haven't actually tested that yet, but there are three reasons why I think CarpetX should be more scalable. And one is that AMREX has been designed for exascale, and they're rewriting the code. They have funding to do that. We don't have that funding for CarpetLib. And they also have a better OpenMP parallelization design than we have in CarpetLib, so there's an advantage. Second, CarpetX can run without subcycling in time. We never implemented that in Carpet. So that, I mentioned earlier, subcycling in time is a difficult algorithm to implement. And if you need it, it makes everything faster, but there are some setups where you don't need it, and then running without it makes codes more scalable. you can run faster. And the third reason, that is what interests me, is that it supports discretization methods inspired by discontinuous Galerkin finite elements, and they need fewer ghost zones. If you have a black hole simulation and you want an 8th order method, for example, that seems to be a good order, then in Carpet you need 4 or probably 5 ghost zones. And that just means you need to copy a lot of data, interpolate a lot of data from coarse to fine grids. And if you get by with only a single ghost zone, that makes things incredibly more faster and efficient. So this is something that I am interested in. Another feature in CarpetX is just that AMREX has been designed with GPUs in mind. We never put that into CarpetLib. We had lots of efforts in this direction, lots of optimizations, but we never actually streamlined enough to make it easy to use, to make it use out of the box. When we looked at GPUs, that was probably 10 years ago, the hardware looked a bit different. The memory per GPU was smaller. It was not possible to access main memory directly from the GPU memory. You needed to copy things over explicitly, etc. But now GPU hardware is easier to use. And since AMREX supports that, then we get that for free. That is quite nice. By using AMREX, you immediately get that feature. And depending on how well AMREX does with GPUs and efficient SIMD vectorization on CPUs, we're also looking at Cocos. It's not quite clear which route we are going yet, but I think we will try AMREX first. And another interesting feature that people have been asking for is new discretization methods. Carpet essentially, well, let's say AMREX has built-in support for vertex-centered, edge, face, cell-centered grids, etc. And that is important if you have hydrodynamics and fluxes. Fluxes should be on faces. And if you have a density, it needs to be in a cell-centered. And if you have electromagnetic fields, a field like an electric field wants to live on an edge. A magnetic flux wants to live on a face. And then you get consistent discretizations. For example, you can calculate the divergence of the magnetic field without any discretization error. That is always 0, exactly 0, well, up to floating point roundoff. And another thing that is implemented efficiently in CarpetX is refluxing. That is, if you have certain fluxes on the coarse grid and certain fluxes on the fine grid, you calculate them in different ways. They might not actually agree. And at the coarse fine grid boundary, you have a certain amount of matter flowing out of the coarse grid and a certain slightly different amount of matter flying into the fine grid. And that's not good. So you don't conserve mass, for example. And refluxing means that after you did both the force grid and all the fine grid time steps, the subcycling, you update all the flux terms and the corrections to make sure that everything is consistent, and then you exactly conserve mass. It's currently not reasonable to put a mesh refinement boundary inside a star, a neutron star, where there might be a shock wave with Carpet. I hope that with CarpetX that will be possible. We haven't tried that yet. And CarpetX also has other algorithms, for example, multi-grid solvers. Eloisa Bentivegna implemented a multi-grid solver in Carpet. I haven't seen much use yet for some reason. I don't know why. I think it's a really exciting thing. So I tried the one here in Carpet in AMREX, which is really nice. And because the one in AMREX is second order accurate, so if you want to do some hydrocode, it might be good enough. But if you want to have an 8th order space-time evolution, you can't start the second order AMREX multi-grid solver. So that there's still some work to be done. But at least there's some support in the framework, so we don't lose what we have in Carpet. I want to briefly describe the parallelization in CarpetX in AMREX. It's slightly different from the way Carpet does it. So here you have on the left the coarse grid and 2 fine grid blocks. And these blocks they could live on the same process, or they could live on different MPI processes. And OpenMP parallelization then works on top of that by splitting each block into a set of tiles. And all tiles have the same size, for example, 8 cubed or 4 squared here in that graph that I'm showing here. And then, well, they should actually use 8 different colors. So you could run efficiently on 8 different threads here, or maybe on 2 processors with 4 threads each. And I also showed you the ghost zone picture before, which shows how ghost zones work and which data overlap and which don't. For example, you see that Around each of these blocks, there's ghost zones, but the individual OpenMP tiles do not have ghost zones around them because you just can immediately access the data assigned to the other OpenMP tiles. That's the big advantage of OpenMP. It's shared memory, so you can access data that another thread is using. You need to distinguish between data that is read and that is written. So data written by one thread cannot be accessed by another thread in any way. That's inconsistent. But data read by one thread can be read by another thread as well. That works fine.
Hey, Eric?
Yes, yes.
Does Amrex have some particular understanding of how to make use of NUMA in dividing these tiles up and in parceling out data to different OpenMP threads? Is it NUMA aware at all?
I do not know.
Okay.
I've seen the OpenMP loops, and the OpenMP loops essentially treat all the tiles here the same way.
Okay.
So I guess if you wanted to use a NUMA system, then you just run 2 MPI processes on it. I haven't seen anything with regards to NUMA. Maybe it could be added. I think they don't.
All right.
Don't quote me. What is the, someone drew a green line onto my slide. Yeah, serves me right. I did the same earlier. I was the second one to draw something. So this is about the parallelization. Each of these tiles that you saw earlier should be small enough that it fits into the L3 cache of a CPU. And what that means, once one thread has started working on one tile, everything fits in the cache and can be accessed very efficiently. So if you have a hydrothon and you want to loop several times over a tile, you do that efficiently because all the tile memory is already in the cache. For example, to calculate fluxes, you might first loop in the X direction, then in the Y direction, then in the Z direction through the flux updates, and it works beautifully. Or maybe you want to first loop over a tile to run cont2prim, and later you want to do something else. Maybe you need temporary variables. You don't need temporary grid functions. You just need a thread local array as big as one tile, 8 cube points or something that you can do. And that is very efficient. It's basically the best way of doing it. It's also efficient on GPUs, where once you loaded data into the fast memory, you act on the data as often as possible. So when you schedule a function call, it should work on a single tile only. That's different from Carpet. In Carpet, you're supposed to work on a whole box and do your own OpenMP parallelization. In CarpetX, not anymore. There, you're supposed to not do any OpenMP. You just run a single thread and do work on a single tile here. I already mentioned my personal interest, where it reduces the number of ghost zones earlier. Not going to describe it again. And fun fact, we're now requiring C++17, and now the Einstein toolkit that's used by many people is more conservative for good reasons. But when you develop new code, then you really want to have that new features. And C++17, it's just the additional data types you get from the STL, makes the code simpler and safer. So we're doing that. And quite frankly, this is 2020, 2017 was 3 years ago. The basic contents of the standards were well known before that. If you have a C++ compiler that doesn't support that, then I recommend installing CCC or Clang or asking the system administrator to support one of these. They're basically available everywhere. I'm too old to handle all these compilers for the different vendors that don't properly support the C++ standard and so on. At some point, it's just not fun. And the future lies in Dockers or containers anyway. It has so many advantages. So in the future, you probably just put the code in a container and an image and run there. And it doesn't really matter what the system installs because you get your Ubuntu 18.04 with GCC 8 and everything's fine there. I think I'm ranting. I'll stop now. Movies, yes. Hey, very good. If you made it so far, I'm now going to show you some movies. And I just realized that's the first time I'm showing movies over Zoom. Let's see how that goes. So this was the first movie I ever made with CarpetX about a year ago. Let's see how that looks like. It's a scalar wave equation, and the wave moves from left to right. It's a completely periodic domain. And you see some artifacts here. I think some of the blocks are from the movie, but yeah, the weird vertical stripes that you see here, they are because at that time there were still lots of bugs in the code. And you also see at the upper and lower boundary, you see weird things. These are actually bugs in the visualization. I ran this with a cell-centered grid, and then I put it into a visualization toolkit visit, and visit tells me it can only handle vertex-centered grids, not cell-centered grids. So it wouldn't work. So I told visit, don't worry, it's a vertex-centered grid. And it visualized something, but of course at the boundaries, everything is wrong. So that wasn't that good. So we needed to fix that. That movie has only historical interest. You probably don't care about that. There's another movie, but no, next page. Now we have a movie with AMR, where AMR actually works, where you see a wave moving outward, and you see also the grid structure adapting automatically. And these adaptations of the grid structure, you need to write a function that says how much resolution you need in each cell, and then MREX does the rest. It decides where to put the refined grids and where not. Let me show it again, how the thing moves outwards. Yeah, as this wave moves outwards, of course, the amplitude decreases like 1/r, I think, which is why the color scale updates. And of course, if you use adaptive mesh refinement, you can also use too much adaptive mesh refinement. So here you see the initial grid, and you see already that the boundary is a bit refined for some reason. So what happened here, I had a slightly inconsistent boundary condition. I put a Gaussian on it, and if you put a Gaussian on a periodic grid, then of course at the outer boundary, there's a slight kink there. So the AMR noticed there's a kink, and then it tries to zoom in to find out what's going on there. Because it shouldn't, nobody cares about that outer boundary, only wanted to refine in the interior. That's a very quick movie because I requested too much accuracy, and by this time, because the whole grid had been refined as only fine grid, and that makes it incredibly expensive. I think this has 3 levels. So refinement is a factor 4 in every direction. So 4 to the third is something 64. Yeah, that simulation by that time was 64 times as expensive as it should be, both in terms of CPU and memory. So I had to abort that. So it is just, I mean, if you use adaptive mesh refinement, it's a really cool tool. But if everything is automated, it doesn't mean everything's correct. It just means that it can be wrong in different ways. But here, and next I wanted to investigate the edge, face, and vertex-centered things. And you can't really do that with a wave equation. There's just one scalar. And Einstein equations are way too complicated, so I implemented a token Maxwell system to see what happens here. When you see several levels of grids, there's probably a coarse grid that is not visible. It's refined everywhere, and 5 levels or something. And this is a wave. It's a very thin wave. It's in principle a Gaussian wave, but it's squished. And it's an electromagnetic wave. This is a 3D simulation. You only see one cut, periodic boundaries, and then see as it moves. And you see how it refines when the wave comes in and de-refines when the wave leaves. And that all looks quite nice until actually it goes out on the right side and back in on the left side. And then the first strange things should be appearing. Yes, now you begin see various places where AMREX starts to refine in places where you think there shouldn't be any refinement. And the reason is that actually the solution does not look good. If you just look at the visualization like that, everything looks fine, of course. But if you look at the details, there are lots of problems. In particular, this is a 2D cut. If you look in 3D away from that, at the corners of the domain and so on, there are lots of problems, and it is completely unstable in many different ways. And at that time, although everything looks superficially nice, there were still lots of bugs and inconsistencies and undefined grid points in exactly the same way I mentioned before, right? The main advantage of CarpetX that I advertised, that it keeps track of things, that was the work that told me that even I cannot get it correct. And you fix one bug and another bug appears there. So you need the rigorous tracking that everything is defined, nothing remains undefined. And we implemented that, and luckily Steve Brandt had put the respective work in the flesh already, so now we're benefiting from that. And I mentioned Steve Brandt, there probably were other workers as well. It's just that over the years he has pushed that to me, which is why his name is in my mind. And so yeah, no, this has all been fixed thing, of course, but yes, go on.
So the other people who've worked on that are Sam Cupp, our graduate student, and Roland Haas.
Okay, yes. Apologies, Sam and Roland, for not mentioning your names. And yeah, but after fixing that, I wasn't actually interested in the Einstein equations. So after fixing that, I moved on to the Einstein equations, implemented the Z for C formulation. And you see now a movie. These are two black holes. What you see here is the lapse function. The lapse function is 1 far away from black holes and 0 at near the center of the black hole, whatever that means. We're using coordinates and so on. And then you see the black holes moving. Man, that movie plays quick. Apologies. So let's play it again. So this is about 1/4 orbit, and these black holes should make 3/4 an orbit and then merge, but the movie is too short. And I also, at that time, it didn't have an apparent horizon finder yet, so it's not clear where the apparent horizon is, but it's where the lapse is about 0.3 as a rule of thumb in these kind of gauge conditions. So the horizons are probably here and another horizon here. That's just the equatorial planes of two black holes orbiting. And is there another movie? Another movie? Yes. And this is now testing the hydrodynamics. This is taken from the public THC code. There's an advection equation in there. Advection equation is kind of a simplified hydrodynamics. You prescribe the velocity field. The only thing you evolve is the density. So the density is 0 everywhere, and it's 1 inside one of these square boxes or cube or whatever that would be in 3D. And there's some mesh refinement boundaries, and then you push the square across the grid. And of course, the trick is you have this density discontinuity. How well is this handled by the code? Do you get oscillations? Is the cube completely smeared out? Is it lost or whatnot? And you need high quality, in this case, shock capturing methods to get this correct. So let me play that. And you see it moves. It keeps the shape approximately. It's a bit smeared out at the boundary, but only by a finite amount. It doesn't keep getting more smeared out. And what I find really cool, inside the cube, it de-refines, because the code realizes that inside the cube, you don't need any additional resolution, because inside the cube, the density is constant. It's 1 everywhere. So you don't need any mesh refinement here. And then, of course, it beautifully tracks how the cube is erected. Okay. What? Okay. So after showing these movies, I want to describe the current state of CarpetX. I mentioned we started with a heavy lifting about a year ago. The basic infrastructure works, as you saw. We have adaptive mesh refinement, regridding, I/O, interpolation, etc. We have basic numerical thorns. There's the ODE solver to solve for the time evolution. There's a Poisson solver using multi-grid equations, and we have some proof of concepts physics thorns. There's a Z for C thorn for the Einstein equation and apparent horizon finder, the advection equation solver from the THC thorn, and some space-time initial conditions. And I say this is a proof of concept because these things have not been rigorously tested. Kind of, oh, you say this is 8th order convergent. Let's test that, and then making sure you get exactly the same results as with the other codes who claim to solve the same equations using the same computational methods. That has not been done. It looks reasonable what I showed you, but movies are not proof that anything is reasonable. The next steps in terms of infrastructure would be checkpoint restart. That's not yet implemented, so you can run until you run out of queue time, maybe for a day, but big simulations take much longer. We need to fine tune efficiency and scalability, check how it runs on 10,000 or 100,000 cores. Want to implement subcycling in time. That is in Carpet, not yet in CarpetX. And some people want across the axis boundary conditions for spherical grids. That's up to the MREX team. They said they would have the corresponding grid copy operators. They would implement that you need for this operation. Want to improve I/O efficiency, scalability, and we want to finally run on CPUs and the GPUs and see how that goes in the code. In terms of physics, of course, I showed you the Einstein equations and an advection equation. There's not yet the GR hydrodynamics code. That's clearly one of the next steps. We want to implement wave extraction so that we can actually get the gravitational wave content out of a simulation. That should be straightforward to do, but still needs to be done. And as I mentioned before, for all the don'ts that are written, you need to check correctness, compare accuracy versus cost with existing codes. Hope that it is actually faster than Carpet. I'm quite sure it is, but who knows? That there could be a simple bug that we have in there that prevents all these things from happening, but that's necessary. And in the end, in case I don't have material for my thon, I want to point to two other things, but I'll mention these after the questions or discussions. One is Caliban. That is a tool that simplifies submitting jobs to remote systems or to the Google Cloud. I'm quite a fan of that. I ran the Einstein Toolkit on the Google Cloud platform. That was quite simple. And the other is I want to advertise the Julia language, mostly because in our local Gravity meeting, people teased me that I'm using Julia, and they said, well, if it's so good, could you implement the Einstein equations in Julia? And I said, yes, of course. And the answer was, well, why haven't you? So I guess I have to at some point. With this, I close my presentation and I invite your questions and comments, of course. I'm full screen. I can't really see things here. Is there a moderator who wants to handle the questions in the chat?
Yeah, I can help with that. I don't see any questions going through.
There's a few raised hands. Let me unmute Mario. Go ahead, Mario.
Oh, hello.
Hello.
Yeah, I have two quick questions. I'm not sure if you mentioned this in the talk, but let me just ask anyway. One is CarpetX, when it's available, will it be open source?
Oh, it is open source. I forgot it. There's a URL on Bitbucket. You can look at it right now.
All right, thanks. And the other question is this, does it implement the moving box mesh refinement technique as other Carpet AMRs, or is it more like a more dynamic AMR implementation?
It's true dynamic. It's a superset of what Carpet does. So, of course, what I mentioned before is that you tell MREX which boxes, sorry, which cells want you to refine or not, and depending on that, it refines the boxes. But for example, for the black hole simulations, I don't recall what it did, but there's certainly a test case where you just say where you want things refined, and it refines a region around it, and that's the same way Carpet Regrid 2 works. You probably don't get exactly the same grid structure, so if you want to do a one-to-one comparison, we have to put in a bit of work to make sure that it refines exactly the same cells and so on. But in principle, it's there.
Yeah, sounds good. Yeah, from the animations, I saw a little bit of a more dynamic AMR, but I just wanted to be sure. Just wanted to ask anyway.
Yes. So, I mean, some of them were dynamic, but for example, for the waves that just moved left and right, that essentially is the same you would get with Carpet Regrid 2 as well. It just refines near the wave that is moving.
All right. Thanks so much.
All right, please mute yourself. Oh, thank you. Next question, next raised hand is from Eloisa.
Hi, Eric. I have two questions myself. So the first one is, will you still, with CarpetX, have access to low-level grid operations to do manually in your code? Or will all of that now be hidden inside MRX?
It's approximately the same as in Carpet. In Carpet, you have Carpet and Carpet lib, and the low level, you have to call Carpet lib. And you can now call MREX in very much the same way. So there's a data structure in Carpet. In Carpet, it would be GH or DH, and that has all the pointers to the AMRX variables, and you can just look in there and do the low-level operations if you want.
Got it. Okay, thanks. And the second thing I wanted to ask, it's more maybe a bit of a reflection. Does this imply that most of DET will need to be rewritten in order to leverage CarpetX?
The plan is not to. So at the moment, CarpetX is at a state where we just develop it and we don't really pay attention to backward compatibility. But Roland has recently been stepping on the brakes and saying, no, we don't want to rewrite everything. People don't like it. And yeah, so in my mind, the most important thing about the Einstein Toolkit is the user community. I mean, we don't have the fastest code and the shiniest code and so on. It's just we have a very robust code that can do many things and many people that use it. So the most important thing is not lose the people and the effort they have put in there.
Definitely.
And MRAX makes certain things a bit different. For example, it likes cell-centered grids, whereas Carpet likes vertex-centered grids. So there is some bit of impedance mismatch, but we've already begun to look at extending the flash a bit, writing macros and so on, where you can, I mean, a reasonably written Carpet code, and it should work with CarpetX out of the box. I mean, there are of course codes to do something really special that will have to be adapted. But if it's just a straightforward initial data tool or Tron or something that evaluates the right-hand side, that should work out of the box. It probably doesn't yet, but it should.
So we have a question in chat which is sort of similar to this, and I just thought I'd read it here since it's similar. How much work is needed for Thorn developers to port their codes to CarpetX? So I think we're hoping the answer is none.
Well, it's not none, because CarpetX really insists that you declare reads and writes statements. So you have to do that. And I think that's really good. People should do that anyway, but that is necessary. And of course, that also means that the Thorns do things consistently, right? I mean, they don't just randomly access points in a way that can't be declared. And the other thing is the OpenMP parallelization. I mean, either you switch OpenMP off altogether, or at least you switch it off in your Thorn. And the hope is that once you're done with that, and if you don't do anything fancy behind the what? Without Cactus knowing, then it should work.
All right. We've got another hand raised.
There was a Bruno, looks like he either logged off or he lowered his hand.
Right.
Sarita?
Surrender.
Hi, so I do have few questions. First, can you again please briefly explain the main difference in the parallelization between Carpet and AMRX?
Okay, let me try to go back a few slides. And yeah, I'm in this full screen mode. So I think this is the main difference. So Carpet does two levels of parallelization, MPI and OpenMP. MPI is between the nodes and OpenMP is within a node. The MPI thing is exactly the same. There's no big difference. Same ghost zones and so on and so forth. I mean, it will split the grid in a different way across the processes, but it does the same. The difference is in the OpenMP parallelization. In Carpet essentially does no OpenMP parallelization at all. It gives you large boxes to a Thorn, and the Thorn has to parallelize looping over that grid by itself using OpenMP. And CarpetX now does that by itself. So it takes each of these large blocks and splits it up into individual tiles and does the OpenMP parallelization there into tiles. And then the Thorn is not supposed to do anything with OpenMP. Instead, the Thorn only sees one tile at a time and can do whatever it wants on the tile, can iterate over it multiple times and so on and so forth.
Okay, now I get the reason as to why you asked us to switch off the OpenMP.
Yes. Now thinking about it, in principle, of course, we could just switch off the tiling in CarpetX. That's probably not difficult. It's probably a runtime flag. But it's kind of a global thing, so you have to make sure how things meshes together. Okay, but the new way is more efficient, definitely. So it's a good way to go that way.
And also, I didn't get this. So did you do a scaling test or yet to be done?
I did a scaling test up to, I don't know, 1,000 or 1,500 cores and so on. And there it looked reasonable. It looked well. And I did see some loss of, I mean, in principle, for some reason, MPI scaling is always better than OpenMP scaling. I think it shouldn't be, but in my experience, that's always the case. I think many people experience that. And when you go to, I believe, 1,000 or 1,500 cores, then you find that OpenMP scaling becomes more efficient. So then you run, say you run on 1,000 cores, then you want to have, say, 250 MPI processors and 4 threads. Whereas in principle, of course, you could use 40 threads per OpenMP process on our system, but that's not the most efficient.
Okay, and the last question, sorry for so many. So recently I've attended this talk where the SXX people have been proposing this idea where they could use different discretization and time integrators at different parts of the grid because they want to start simulating binary Newton star merger and their current discretization scheme can't handle the shocks. So is something that's going to be implemented in the Einstein toolkit, like using different discretizers at different places, so that to speed up the like to get to reduce the computation sources, so that you can get good conversions.
Yes. So we have always put a lot of effort into making sure everything is consistent numerically. You get high convergence near mesh refinement boundaries. I don't exactly know what you refer to with the problems of SXS, but I believe it was their idea that you want to do special things for fluxes and for reconstruction at the boundaries of their boxes. And the question is whether you can get by with a single ghost zone there or whether you need multiple ghost zones. And the methods that we would be using in AMREX are standard methods that have been around in mesh refinement for many, many years, and that are available in other AMREX-based codes as well. People use that. It has to do with refluxing and having more than one ghost zone and so on. So in that respect, I'm not aware of any problem that could be hiding. Famous last words. Right.
No, so the thing is, they can't really use the spectral scheme for shocks, right? So they're planning on using finite differencing where there are shocks, tracking them, and then using spectral at the rest of the domain. So
Okay.
so that so I'm thinking like what they plan is to get a good conversion. Like use less computational resource at the rest of the grid because they're using spectral. Because they can get it at lower orders and use finite difference at those places where they can't really use spectral. So I was thinking is something else being taught in ETK similarly.
Yeah, so the Einstein toolkit traditionally has been using finite differences for spacetime and finite volumes or similar for the hydro codes, and not really a spectral code. There's the one paper I mentioned where Jonah Miller, my former graduate student, worked on code that gives you a bit of spectral accuracy and reduces the number of ghost zones. And that works beautifully, of course, for spacetime. But when it comes to using that for hydro, there are indeed open research problems, even in mathematics. How to do that in 1D is unclear. So I say the standard methods that we're using in the Einstein toolkit, they work. Using a scheme similar to what the Spectre is using, I have experimented with similar things, but I'm not sure how that would work with hydro in the end. So the thing I've thought about is if you have, say you want a 7th order method, then you split up your grid into blocks that are 8 cubed. That's why I say 7th order, 8 cubed. And then you use a spectral method within each block, and then you need to couple these blocks together. And that works. I've tested it, and it works for smooth systems. And I don't know whether it works for hydro, and that probably means it will run into the same problems as Spectre, as the SXS group.
Okay, let's move on to the next questioner, Roland Haas.
Hey, okay. So just out of curiosity, did we actually ever manage to port an existing Einstein toolkit Thorn over to CarpetX? And I think right now we didn't, even for the really trivial ones.
It's a good point. So many Einstein toolkit thorns are not quite cleanly written. So we would first have to clean it up. For example, if a thorn sets all the points to 0, and then very often it doesn't loop over all the points and sets it to 0. Instead, it calculates the number of points and uses a mem copy or some nonsense like that. And that would not be a good idea. It breaks the OpenMP parallelization scheme of AMREX. So we would, I think, first have to write a very simple bare bones tutorial level thorn, say the wave equation, and then use it. I think it would be a very good exercise, because if that fails, it's probably something that could easily be fixed in some way.
Right, so I think it would be good to kind of have, okay, this is a sample thorn that works with both, and this is what you have to do.
Yes, very good, very good. That we should do that.
All right, thank you, Roland. Zach. You have a question?
Yeah, so related to that, thank you for the, wow, a lot's been done over the past year. This is awesome, Eric. So related to Roland's question, could you maybe provide a link, sorry if I missed it, a link to the source code of the latest CarpetX? It is open source, right?
Yes, yes, it's on Bitbucket. It has been there from day one.
Yes.
I don't know, Roland, can you post it in the chat right away? Because it's embarrassing that I don't have it here. It's probably Bitbucket, eSchnet, Cactus Amrex or something.
Awesome. I almost think this should be like featured prominently somewhere on the Einstein Toolkit website, just so that folks know, you know, we are working on this next generation piece of code. And the thing is, so related to that, you know, if I could see how these CarpetX thorns are written, I could teach NERPy how to generate them automatically.
Yes, yes, yes. So the thing is, over the time, of course, there have been 3 or 4 different ways of writing these thorns, because there's this vertex-centered and cell-centered difference and so on. So we try to abstract some things away in C++ to make it easier for people to write it. But that's something that you don't care about because you just Pythonize it and then it works anyway. So.
Yeah, nice. And so very much related to that was my second question, which is there a plan to support staggered grids?
Yes. So what I called vertex, edge, face, and cell-centered, that's also called staggered grids. Okay. So Amrex is by default cell-centered. You see that on the picture here. And each of these points can be moved in any direction by half a grid spacing. So there are 8 different ways of staggering. Yes.
Well, that's awesome. Great. So
yes.
Illinois GMHD's staggering for the vector potential might conceivably be doable with the infrastructure now.
Yes, yes, it should be. It should be.
Okay, that will be very exciting. Can't wait for that. Okay. And my third and final question, very quick. Which formulation of Maxwell's equations did you use?
Of what equation?
Maxwell's equations. When you were solving, showing the Maxwell evolution.
So yes, yeah. No. I was experimenting with things. I wanted mostly to check out the infrastructure. So I implemented 2 or 3 things at the same time. I think there's one where you evolve A and E, and another one where you evolve probably E and B or something, and I experimented with various ways of staggering. So I'm quite sure that what I have there, it might well be numerically unstable. I mean, it's all consistent and so on, that measure Feynman boundaries, that's good. But there's no proof that energy is conserved in that scheme. I didn't push it further because I don't have the experience, and doing that would take weeks just to get everything correct, whereas in the end,
So I just pasted a link to one of Thomas Baumgart's papers. Terrence, one of my students who I think is on right now, he's going to be giving a presentation on a couple new, or one new Einstein Toolkit thorn written in NERPy that implements these 2 formulations of Maxwell. So one is ADM-like, and that's, I believe, the one that you're using. And it has the unfortunate feature of having 0 speed modes in it for error modes. And the other one is more BSSM-like, and it seems to behave much, much better.
Okay, so you have additional variables in there? I did not do that.
Yep.
Okay, very good. Yeah, no, I think that's necessary.
Yeah, I think you'll find it behaves a lot better. And if you want to learn, if anyone wants to learn more, please do tune into Terrence's talk.
Yeah. So if you look at the current source code, you'll find many thorns, and half of them are probably outdated in the sense that they don't use certain features that have been since become available in CarpetX. There are probably 3 wave toys and 3 different hydro toys in there, just different approaches over the time where we fine-tune the interfaces to make sure what works. And yeah, I've been cleaning up these, but not recently, just removing the old thorns because there's no point in looking at them.
Sure. So yeah, I'll be very excited to take a look at, say, a model thorn, something like what Roland suggested, an eigenthorn, if you will, just to get an idea of what the expectations are, what information it needs. Obviously, yes. It needs a reads and writes, which is not something that's very difficult with NERPy in principle. So yeah, I think we could automatically generate those in AutoWeaver.
Yeah, I think a wave toy would be a good idea.
Yeah, that would be great. Okay.
Okay, thank you, Zach. Federico.
Yes, at first, congratulations for the talk because it was really beautiful and useful.
Thank you.
And now I would like to ask, is the CarpetX in some way agnostic of the coordinates, or because I see only figures in Cartesian coordinates, let's say, but can, for example, the mesh refinement, adaptive mesh refinement be used also with spherical coordinates or other?
Yeah, so the CarpetX and Ambrex, they only care about the topology. The topology has the big Cartesian that is built in that cannot be changed, but that definitely allows spherical or cylindrical coordinates. And the only thing that is missing there is, of course, respective boundary conditions. And I'm not sure whether you want to update the interpolation, the prolongation restriction operators to know about the respective metric elements, or whether you want to store densitized variables or something to make sure that works. But that can all be done. So yes, that is definitely possible, spherical coordinates. Well, it's not yet possible because the boundary condition across the axis, you need to copy points by pi or something in the phi direction.
Yes.
That
Probably,
is missing
correct.
in Ambrex. So this is where we're waiting for the Ambrex developers at the moment.
I see. Thank you.
All right. Thank you, Federico. Next, oh, did I think I accidentally lowered somebody's hand. There was one other question. Yes, Andres, go ahead.
Okay, thank you, Steven. First of all, I would like to thank you, Eric, for the talk. I don't know, Eric, if you are acquainted with other discontinuous Galerkin numerical schemes. They use some subcell limiters, and my question is, if are those techniques used for these numerical schemes, of course, if you're acquainted with that, similar to the ones used in Carpet?
So Carpet does not use spectral methods. The other project that was mentioned earlier is the Spectre method by the SXS group. And I'm not involved in looking at cells or limiters or how fluxes are transported across cells and so on. But I have heard that they had great hopes, and these hopes have not materialized so far. That is not a no-go. It just means that certain parts of the code might be more expensive in the end. But these are spectral methods which are very different from what we are using in CarpetX here. In CarpetX, people use finite volumes and finite differences, and for finite volumes and the fluxes there, it's well known how to do that and how to get stable high order codes and so on. There's a large set of methods that are well tested. So the problems that we talked about earlier are problems with potentially future methods, or problems that other people have been fighting in the past year, but I'm not too familiar with these methods.
Okay, actually these subcell limiters used that are related not to this kind of method, but to finite difference and finite volumes methods, not spectral methods.
Ah, okay, sorry, I misunderstood. So the hydro codes that I'm aware of that people have used with the Einstein Toolkit infrastructure are based on finite volumes, not finite difference. I've heard people talk about other methods, but I don't know whether they have been used. Okay, but more to the point, what the infrastructure uses that I'm presenting here, adaptive mesh refinement and so on, is more or less the computer science part. The numerics is basically independent of that. And it should be possible to implement many different numerical methods on top of this. Now, of course, we have a structured, block-structured grid. So if you want to use unstructured cells, this infrastructure will not work for you. But apart from that, any kind of limiter, right-hand side, and so on, that should work. I mean, in most cases, it should work. I mean, not that the methods work, but that you can implement them on top of this infrastructure.
Okay, thank you so much.
Okay, the next question we have is from Aman.
Hi, Eric. Thanks for the talk. Just a very quick question. So, like in your last slide, you mentioned Julia, and yeah, I've always also found Julia very convenient for coding. So, I wanted to ask right now, is there any association of ETK with Julia, or that's just a future plan for now?
Okay, I mentioned Julia because it's the cool language and because I think it's the future. And if I had developed something from scratch, it would be in Julia. But the opportunity that we had here was to replace a core piece of infrastructure with a different infrastructure that is more advanced, independently funded, has a large group of users, and it's very similar in design. So the questions of whether to switch to Julia didn't pose itself. And at the moment, there is no connection to Julia. I'm using a bit of Julia in post-processing and in certain cases. And people have talked about kind of a Python interface to the Einstein toolkit, where you can write some Python code to run at runtime. And you could do the same thing with Julia, but that's essentially independent of what I presented today.
Thanks.
I see no other raised hands. Are there any, does anybody see any other questions in the chat? Okay, I believe that concludes our program for today. We will try to get a version of this online sometime later today, if you want to watch it then.